Good day, everyone. I'm John Levine of Levine Electronics and Electric. Our speaker today is our own partner, Michael McClellan. He's put a lot of work into this presentation, so I think you'll enjoy it. Levine Electronics and Electric is a manufacturer's rep that covers Georgia, Alabama, Florida, Tennessee, Mississippi, and Arkansas. We have two divisions, a control division and a power division. Please check out our website at l-3.com. Our philosophy is to give back to the industry to make it safer and better for all. We've been trying to do these webinars almost every day to just help our customers have a better understanding and help them any way we can. Michael's been, you can find the videos on our website under resources. We have about 44 of them now. We're known as the transformer, arc flash, grounding and protection experts in our territory. If you have any questions, you can type it in the chat box, and we'll see it and we can answer it during the presentation or after. We also, I believe Michael has some handouts that you can also download if you want to get those. Michael may be doing some poll questions. I forgot to ask him if he was, so stay tuned for those. And at the end, we'll have a short survey we'd appreciate you filling out for us. Certificates will go out within 24 hours after the webinar. With that, I'll turn it over to Michael.
Thank you so much, John. Hello, everyone. Hope everyone is having a great day. Today, we are going to talk about a extension, if you will, of the motor overload thermal model. And we're going to start out, first I'd like to test to make sure everybody can hear me. If you can hear me, type in your favorite band into the chat. I'm also very curious as to our audience's musical taste. So. In order to really understand what's going on today, you should really have seen the previous webinar that Terry Smith did on the motor thermal model, which goes in depth. I am going to skip right over that and go right into RTD biasing for the sake of time. But I have put here on the slide some YouTube videos that I think are very beneficial, as well as the webinar that Terry did a few months ago. The discussion today, and when you get into deep discussions about start, inhibit, and those kind of things, we're really talking about across the line starting. It's not that our discussion doesn't apply to soft starters or drives. It's just a much more major factor when we are attempting to start motors across the line. I have already begun preparing for a webinar sometime in August in which we will discuss specifically the protection of motors when a variable frequency drive is utilized. Okay, it's time for our first poll question. And this is going to test your knowledge if you paid attention in the webinar that Terry did. So you should see that on your screen. If you don't, someone please type into the chat box. And what I'm trying to allude to here is that the thermal model as advanced as it is a one-dimensional means of protection. It only looks at one aspect of the power flowing into the motor. And I'm going to close the poll in a second. Most of you got this right. In fact, 93% of you got this correct. And yes, the motor thermal model, the motor thermal overload model, looks at one value and one value only, and that is current. And it computes everything else from that. We are going to do some future webinars on these other aspects of the motor thermal model. We've already done one on the first key element of this that's stated in this slide, the thermal overload curve that Terry did such a good job with. And we will talk at a later date about things like biasing of the motor because of voltage unbalance, and as well as playing around with the motor cooling time constants, and also biasing of the motor based on the hot-cold curves that we obtain from the motor manufacturer. But today we're going to talk about how to utilize stator RTDs to accentuate our motor protection. And I'm going to put another poll question out there to get us to start thinking. Okay, this is a poll where you can check more than one answer, and I'm sure we're trying to identify here some things that could harm the motor that potentially you cannot get from the thermal model. So I'm trying to get you guys to put some thought into what are the situations in which the motor thermal model fails us. We'll leave that up for another 45 seconds. And while you guys are voting, we'll talk about a reminder that the thermal model is just that. It is a model. And unfortunately, it has its limitations. It does a reasonably good job of computing what we call the TCU, the thermal capacity used. Just so you know, GE Multilin invented this technology. There is a patent on it. I'm fairly certain that patent is now expired, but this was conceived by the folks at Multilin before it was purchased by GE. But it has its limitations. Okay, I'll close that poll. And again, the motor thermal model is just that. It is a model. It does not, without RTDs, it does not give us any real-time data, any real data as far as the temperature goes, which is what kills our insulation. Okay, so where does the motor thermal model fail us? The motor thermal model, as I understand it, in the 369 and 469, it may be different in the 869. I am waiting on an answer back from our mutual friend, Terry Smith. But at least in the 369 and 469, the ambient temperature is not taken into account whatsoever. So a thermal model for a motor in a pump in Antarctica and a motor in the Sahara Desert are going to, the identical motor at the exact same speed and torque will show the exact same amount of thermal capacity used. And we obviously know that that is most likely not true. The heat will dissipate from that motor in Antarctica much faster than it will in the Sahara Desert. Additionally, I spoke to somebody about a month ago who had this happen, and it's a very unfortunate situation. But the motor rewind market is a competitive place, and sometimes there are turnover in these type of shops. And there was a fairly substantial motor that went into a paper mill, and after it was rewound, the fan was put on backwards. And the thermal model, of course, will not account for that. Thermal model looks at the current going into the motor, and that's it. And it is relying on the nameplate information that is input into that motor. And the nameplate information is dependent on that fan being properly installed. Seen this recently at a few places. Sawmills are particularly vulnerable to this. Motors have cooling fins, and that is part of their heat dissipation design. And if things like sawdust or kaolin, other materials of a powdery-like substance that can form together to block the heat dissipating from those fins, that is also going to affect the motor heating and make the thermal model that much more inaccurate. One of the things I didn't mention, which has also happened, is when a motor gets rewound, occasionally the nameplate is not updated if it is rewound differently than the original nameplate. And that can also lead to an enormous inaccuracy inside of the motor thermal model. This slide is right out of the manual, and I'm just going to let you guys read this, and I'm going to talk about it. And this tells us, and we need to emphasize, that a motor protection strategy involving RTDs only is not a viable strategy. The RTDs are a little bit slow to respond. Heat is somewhat slow to make it into the stator windings, especially when it originates in the rotor most of the time, especially in a high torque application. So the RTD biasing is not a motor protection strategy on its own. It is a strategy that goes along with the motor thermal model. When you look at a motor data sheet, there are lots of different numbers, and there are motors like temperature rise over ambient. There are numbers like the motor designed running temperature. Then there is an insulation rating, which can also be called the maximum stator operating temperature. We're going to talk about some of these things in a future presentation, like RTD tripping and voting. This particular presentation is focused on how the RTD biasing interacts with the motor thermal model. But there are ways to configure any of our motor protection relays to trip upon a certain temperature. This is a typical drawing of a RTD. And John, would you care to take over for this slide and explain the differences in a, say, a 2-wire, 3-wire, or 4-wire RTD?
Sure, Michael. Let me see if I can, I don't know if I can get the mouse to actually show up. Like to, all right, what you've got on this RTD, if you notice there's 3 wires to it. I've got a wire connected to A1, A2, and A3. And what we want to know is we want to know the resistance in the RTD. But the issue is we also have resistance in the wire. So we need to compensate. If you see A2 says compensation for the resistance in the wire. And the way we do this, if you look at A2 and A3, they're actually connected together at one side of the RTD. Michael, you may want to show them what I'm pointing to, since you have the mouse. Yeah, right there. So what we can do is we can sit there and determine the resistance between A2 and A3. Let's just say that's a 1/2 ohm. Well, if that's a 1/2 ohm, then I know I've got a 1/4 ohm resistance in each one of those wires. So then when I measure from A1 through the RTD and back to A3, the return, let's just say that comes up at, 7.5 ohms. I know to take a 1/4 ohm away and a 1/4 ohm away from A1 and A3. So I know the actual resistance through the RTD is going to be 7 ohms instead of 7.5 ohms. So that's how a 3-wire RTD works. A 2-wire RTD or thermocouple, it does not have a way to take into account that extra resistance in your wire. And then the 4th wire there is just the shield. Michael, I'll turn it back to you.
That was great, John. Thank you. So this is a table that shows what the relay does with the information coming back from the RTDs. An RTD basically varies the resistance, as John was saying, with temperature. And it does that. The nice thing about this type of RTD is it does that in a linear fashion. So the more resistance that gets sent back to the relay, or more accurately, the more resistance the relay detects, the higher the temperature. And the relay has a lookup table. In fact, this is the exact lookup table that it will translate the ohms into the temperature. Okay, let's get into what is actually going on here and some of our settings. Like I said, the RTD bias is meant to augment the motor thermal model. And here we have a chart that shows us the 3 points that we need to input into the relay, the 469 or 869. And the first point is the RTD bias minimum. And you'll see that in the lower left-hand corner. And that is set to the motor design ambient temperature, which 95% of the time is going to be 40 degrees C. Okay. And you'll notice that on our chart here, if you look at the 40 degrees C, that corresponds to a RTD thermal capacity used of 0. So what this tells us is if the motor reads 40 degrees C, if the RTDs read 40 degrees C, it's going to force the RTD thermal capacity used to 0. Okay. Now the second item that we need to enter is the RTD bias center point, and that is the motor designed running temperature. Okay. The temperature that the motor is designed to run at during a steady state condition. Okay. And you'll see on the chart that usually corresponds to around 18% of the thermal capacity used. Now, in reality, that's a ever-changing number, because the thermal capacity used by the motor will continue to go down to its steady state value if the motor is running at rated speed and torque, because it is being cooled by its fan. It will never return to 0 while running, but it will approach its running thermal capacity. The third number that we need to, and it got cut off here, I apologize when I took the snapshot, but all the way up at the top is the RTD maximum point, and this is, we set this to the stator maximum temperature that we also call the insulation class. And obviously that insulation class is only rated for that temperature, and any temperature above that, we are reducing the life of the motor. So you'll see that this motor has looks like a 155, 160 degrees Celsius temperature class, maximum stator temperature. And you'll see that corresponds to 100% thermal capacity. Here's what it looks like inside of InterVista Launchpad. I know that all of you have this installed on your machine and use it daily. This happens to be the 469. You'll see that there are 4 settings to modify as you set up the RTD biasing. There's the 3 that we just discussed, and then you just need to enable the RTD bias. Inside the 869, it looks a little bit different. There are 2 additional settings to modify the RTD bias voting and the RTD bias voting band. And we're going to have a more lengthy discussion on this soon in a future webinar when we dedicate the entire hour to RTDs and how to set them up. But today, we're going to leave it at the RTD bias voting is very simply a way to prevent inaccuracy caused by a failed RTD, which happens fairly regularly. And when an RTD fails, it fails in the open state. And the open state means lots and lots of resistance. And obviously that would translate into a 100% thermal capacity used, and with some other factors will lead to a trip. So the RTD bias voting requires that both RTDs show a similar temperature so that the open RTD condition does not cause a nuisance trip. Because remember, what we're trying to do here is, this is an art. It's the art of relay protection. And I believe that's why Lewis Blackburn entitled his book, The Art of Modern Relay Protection. We're trying to find a balance somewhere between keeping the process up and running and protecting a motor that may cost, $100,000 or $300,000. But RTD bias voting is a great way to eliminate some of these nuisance trips. In addition, there are some sensors in the 469 I know of that will help detect an RTD failure, and we will certainly discuss that at a later date. Okay. It took a while to research and have several discussions with different people within GE to enable me to understand what is actually going on here inside the relay when we enable RTD biasing. And I'm going to explain it to you verbally first, then we're going to look at this slide, and then we're going to look at a spreadsheet that I made in order to help myself and you guys understand what is going on. So the most important thing to understand is that the thermal model, the thermal overload model, and the RTD bias model are two independent models that are running simultaneously. So the RTD model is not adjusting the thermal model. It's not making adjustments. It's not learning. It has no effect whatsoever on the thermal overload model. It's running concurrently. And then at the end of the calculations, the RTD bias thermal capacity used is compared against the thermal overload capacity used, and the greater of those is what the relay actually uses to monitor that motor. Now, let's step back and look at that. What is that telling us? It's telling us that by adding RTDs and RTD biasing to our motor protection scheme, we are a little more conservative about protecting the motor. So let's go back to let's go back and see how we get the quantity known as thermal capacity used RTD bias, okay? Which is different now, again, from the thermal capacity used, or TCU, of thermal overload model. Okay. In this slide, there are two equations. One of them is used if the actual stator temperature, which I'm going to call T RTD actual, or the actual temperature that the RTD is, that the relay is reading from the RTD. If that temperature is greater than the RTD bias center temperature, which we input before in our relay settings, then equation number 21 here is going to be used. We're going to take the actual temperature and subtract the minimum RTD temperature, take that quantity and divide by the quantity, the center RTD temperature minus the minimum RTD temperature, which is our ambient, remember? And we're going to multiply that by, because what we're getting there is a percentage, okay? And we're going to multiply that by the total, the thermal capacity used at the RTD bias center. Okay? The equation changes when the actual temperature is greater than the RTD bias center temperature to avoid dividing by 0. And so this equation basically normalizes where we are along that chart. I'm going to move back to that slide and show you what I'm referring to here. We are moving along this line, basically. As the RTD, as the temperature goes up in the stator, we are moving along this line. And these equations will help us compute the thermal capacity used in the RTD bias mode. Okay, here's another poll question. I think that's fairly relevant. And that is, what horsepower do you guys install? And hopefully on the line here, we have some plant engineers, we have some consulting engineers, we have some end users, maybe some integrators. But when you're writing a specification, I guess I'm curious, above what horsepower do you specify that the RTDs should be built into the motor? I'll leave that up for another 60 seconds. Now, RTDs can be installed in a lot of different places in the motor. And obviously today we are focusing entirely on the RTDs in the stator. But there are many times RTDs are specified in the bearings, for instance. Okay, thank you so much for your votes. Okay, so now I'm going to show the spreadsheet that I attempted to create. And this should be one of the handouts. If it's not, please let me know. So let's take it from right to left, which is, I think, the easiest way to understand what I'm trying to do here, what I'm trying to show. At the end is our output, all the way to the right, and that is our thermal capacity used. In order to get that, we're going to compare the thermal capacity used in the RTD bias model against the thermal capacity used that is calculated by the overload model. The greater of those is what the thermal capacity used is what the relay is going to see and use. So I'm trying to show that those go into a comparator and the greater of the two comes out. Before that, we have to calculate the thermal capacity used of the RTD bias. And as I was saying in the previous slide, the formula is, first we look at the actual temperature of the stator, and if it's greater than the RTD center point, we use one equation, and if it's less than, we use another equation. So I've got a big long if-then statement in this equation, and I've got some inputs over here to the left that we're going to play with for just a second to kind of see where we would end up. And so, why don't we take the case of, the fan being installed backwards, in that case, we would probably, let's say we're running at steady state, and maybe our thermal capacity used in that motor, if it's been started, let's assume across the line, and it's been running for, say, an hour. The thermal model would tell us that the thermal capacity used has decayed quite a bit, and it's close to the steady state thermal capacity being used. But that's not the case in reality, is it? Our fan is on backwards, okay? So as our actual temperature goes up to, say, 1 Well, we can use 150. Let's use 150 for now. Our thermal model is sitting here telling us, well, hey, we're only at 20%. Everything is fine. But our thermal capacity used according to our RTD bias model is now going to be 83.6%. Why does this matter? Why do we care? Well, if you stopped that motor right now and you waited less than 30 seconds to start it again, if we only had the thermal overload model, this 20% would most likely not pick up our start inhibit function. And this motor would be allowed to start, and this motor would drastically and dramatically overheat in a short amount of time and most likely destroy the stator windings. Because of the RTD bias, we've seen that the thermal capacity is actually 83.6%. Remember, we take the greater of those two values, and now our start inhibit, because it's looking at our value here right under the blue cell, the thermal capacity used, it is not going to allow that motor to start. And it's going to save us the $100,000 to rewind that motor in 48 hours, as well as the 2 or 3 days of lost production time. Let's take another case where maybe the fan is installed correctly. Let's change our actual RTD value to 60 degrees C, which is just above our ambient, 20 degrees above our ambient temperature. You'll see here that the temperature, the thermal capacity used from the RTD bias model shows 4%. However, our thermal model, because we've started that motor a few times, and that it shows us that we are at 20%. And so the thermal model this time is protecting our motor. I've color coded a couple of these cells to try to make it easier to understand. Of course, we can play with the actual temperature of the RTD. That's the one number we should play with while using this spreadsheet. The numbers in blue are the inputs that we need to put into the relay from the nameplate of the motor. The total capacity used at the RTD bias center point, which I put in here, is 18%. This is not a user input quantity. This is a quantity that is calculated for you by the relay. So, and for the purposes of this discussion, I just made the thermal capacity used in the overload model a manual setting, just so that we could play with the values and see kind of who comes out on top. So I knew this was going to be a little bit shorter because it is so narrowly focused, but maybe we'll have a few questions. To summarize, the RTD feedback is a measured quantity of the stator temperature. It is a very useful complement or a supplement to the motor model. It cannot really be used in fast changing conditions because the heat transfer is fairly slow in the motor, and there are situations in which by the time the RTD's detected, the increase, it may be too late. So the thermal model is our number one and primary mode of protection. We did a little poll, but it's up to the customer, the end user, the water treatment plant, the consulting engineer to make the engineering judgment on what, compared to the price of the motor and the price of the downtime, what is the when should RTDs and RTD biasing be specified? And finally, we will get into this again at a later date, but the RTD biasing thermal capacity used on its own and not initiate a trip. There are settings in the relay that can change that, but by default, the RTD bias model cannot be used to initiate a trip on its own. There needs to be another factor there, such as high current, the current pickup, to detect that the motor is in overload status. So that is all I have for today. Let's take a look at our questions. Okay, Led Zeppelin, that's fantastic. ABBA, okay, good. I didn't see that one coming. Yeah, ABBA is fantastic. Could you show us the results of the horsepower versus the RTD question? Okay, sure, we can do that.
I just put it up. Oops.
Okay, hopefully you can see that. We are sharing the poll results. 29% of you said above 250 horsepower, you would put RTDs in the motor. And then 24% of you said above 500 horsepower. And only 12% of you said you would wait until you get above 1,000 to have the RTDs installed. Let's see, Andre Rue Orchestra. Okay, that's a good one. Grateful Dead. All right, excellent. I think I've been introduced to some guitarists lately that are enjoyable. Derek Trucks and Danny Gatton. These are lead guitar players. Do a lot of jazz guitar. But if you ask me which concert I had the most fun at, that would be Air Supply. So, okay, here's a question that I cannot answer. Are the RTDs easily replaceable?
I can answer that for you, Michael. The answer is absolutely not. They're buried inside the stator. So you would have to take the stator apart and replace the RTDs that way. Typically, we've got 6 RTDs in a motor, and they're located about a third of the way in from each end. 2 are on A phase, 2 are on B phase, 2 are on C. That trip voting, we typically have 1 and 4 vote together, 2 and 5, 3 and 6, hoping that those are on the same phases. So no, you cannot easily replace an RTD. And if you're going to specify RTDs, the most common today is 100 ohm platinum. Try and stay away from 10 ohm copper. The resistance in that wire that I was talking about can only be 25% of the total resistance. So if you have over 2.5 ohms resistance on a 10 amp copper, it's not going to read right.
Okay, another question came in. Is the most common practice to use 6 RTDs and use the other 3 as spares to swap?
Kevin, I think y'all are only putting 6 RTDs. I don't think you've got 9 in the stator. If you do, that's actually a good idea. So you'd have 3 per phase. So if one of the ones goes out, you could use the third one. The problem with RTDs when they bring the wires back is you never are really sure what phase RTD is connected to, because there's just a bunch of wires brought out of the terminal block. So, typically what we see, because we have 12 RTDs available, we have 6 in the stator, 2 on the motor bearings, 2 on the pump bearings. Then we have 1 on a pump case if you've got a pump case. And the last one we use for ambient. One thing is we can use on both 369, 469, and 869, that ambient can be used in the thermal model. It's not part of the RTD biasing, but it is used in the model. Kevin wrote back that they can get 9 RTDs, so that's good. Do all 9 RTDs as stators if you don't need to use the others.
Well, I thank you all so much for being with us today, and thank you for participating. There may be a short survey at the end. We'd love for you to tell us what topics you would like to hear about. If you like these webinars and would like for them to continue, please buy some Multilin 869s. Thank you so much for your time.
Thanks, everybody.